In this video, I'm going to show you how to build and sign and then transmit a Bitcoin transaction using Go. We are going to be building a so-called SegWit transaction, and SegWit stands for Segregated Witness. SegWit is an improvement to the Bitcoin protocol that was implemented a few years ago. I don't remember the details. What it boils down is mostly that the signatures for the transaction are not stored on the blockchain, but they are stored somewhere else. If I remember correctly, that's it. And this way they are much smaller, so they have lower transaction fees. We will be using these libraries called BTC Util and Argon2. We will be using BTC Util to work with Bitcoin, with the Bitcoin protocol, with Bitcoin keys, addresses, and so forth. And we will be using Argon2 to derive keys. There are better ways to derive Bitcoin wallet keys, but we are just going to use Argon2 for simplicity, because I don't want to delve too deep into like the traditional ways to derive wallets. And then this is a part of my Bitcoin series. The code is not exactly related to the earlier videos, so you can just follow along this video from scratch, but I will be following my notes, which are available on my blog moros.dev. So without further ado, let's start writing. I'm going to start by creating a directory called Bitcoin transaction Go, change into this directory, and then call gomod init github.com moros/bitcoin transaction Go. And I'm going to initialize a Git repository. Okay, and then we can install these libraries. I'm going to install BTC Util, and I'm going to install Argon2. Great. So now we can start by deriving some keys so that we can derive addresses. So we can do this using Argon2. I'm going to open this project in a code editor, and I'm going to add a file called main.go, and it's going to belong to package main, and is going to have a function main. But I'm going to store the secret key base in here, except that we need to generate a secret key base first. So I'm going to do this using OpenSSL. As we can see, it has a lot of commands. I'm going to call rand, and I'm going to encode it as hex, and it's going to be 64 bytes long. And then every time we run this command, it's going to give us it's going to give us a different seed, but every time it's going to be 64 bytes long. So I'm going to copy this seed into the clipboard. This is a Linuxism, and I'm going to call hex decode string like so. And we can just print the secret key base again as hex to see if it's correctly decoded. Okay, go run. Okay, so this is printing the same binary again, and it's encoded as hex. And then we're going to have to derive two keys. Let's say Alice wants to sell money to Bob. These are the popular names used in cryptographic tutorials. So I'm just going to derive Alice's seed using Argon2. So I'm going to say Alice seed equals Argon2 ID key, and it's going to be derived from secret key base, but we need to pass a salt, and this salt is going to be a string, just a string called Alice. You can just call it Alice. And then the next arguments are arguments related to the derivation function. So it's going to be 2 iterations with 64 megabytes of memory minimum in one thread. And the last argument is the length of the desired seed. And then I'm going to print this seed as proof that we now have generated a derived seed. Go run. Okay, and then every time we run this program, this is going to be the same. And this is very important because we need this to be deterministic. And then I'm going to create a master key from this seed. I'm going to call master error equals hd keychain. That's from BTC util hd keychain. New master with this seed of Alice seed. And then we're going to be using the regression testing network. So I'm going to store the network params for regression testing in a global variable, net params, like so. This is an oversimplification, but this is like the easiest way to write it in a program like this. And then if an error occurred whilst we were generating the key, we log fatal. So we abort this, we abort the program, and then we can derive a public key from this. So let's say public key equals master EC pub key. Oh, and this is also going to return an error. So if there was an error, we abort, and then we can print pub key serialized compressed, and this is going to print this key in a so-called serialized form. We can see that it is 1 byte longer than the seed, so it's 33 bytes, and it has a prefix of 03, and this 03, or so these serialized public keys begin with either 03 or 02, and based on this compressed public key format, it is possible to derive the uncompressed public key. And as we can see, it's also completely different from the seed, because this seed is only used to generate a private key, and this private key is derived from this seed. So, okay. And then we could actually also print it in a different format but maybe more familiar to some of you. Does it have like a string, or? I think you can try. Okay, apparently not. Great, and based on this serialized, based on this compressed key, we can generate an address. And an address is going to be based on a hash of this public key. So I think it was called, I have to look at my notes, sorry. Yes. Okay, we're going to have to call BTC util hash 160. And what this does is it runs 2 hash functions. One is called repemd, RIPEMD 160. And the other one is called SHA-256, and this SHA-256 is called first, and then the RIPEMD 160 is called on it. And we hash the compressed key, and then we create an address like so: error equals btc-util new address witness public key hash. We pass the witness program, and then we pass the network params for the regression testing, and then we can print the address to the terminal. Let's see. So as we can see, the first line is the seed, the second line is this is the compressed public key, and the third line is an actual Bitcoin address. And we are going to be repeating these steps. So I'm going to refactor it into two functions. I'm going to call one derive master, and I'm going to give it a seed, like a base and a salt, which are going to be bytes, and it's going to return an HD keychain extended key and an error. So the seed is going to be argon 2 ID key, base salt 2 46 megabytes, 1 thread and 32 bytes, and then return HD keychain new master from this seed and network params. And then from this master we can build an address. So master address, master to address, and that's going to take a key, which is going to be an HD keychain extended key, and it's going to return a btc-util address and an error. Sorry, like so. So this is also going to be a pub key and error, master ec pub key, no, key ec pub key. If error is not nil, we return nil and error, and we can return nil because btc-util address is an interface, so it can be backed by nil. And then we do the same thing. We build a witness program, and we can just return this btc-util new address witness public key hash. So we can say Alice master equals, or Alice key equals derive master with a secret key base and the string Alice, and then we can remove this, and then Alice address is going to be master to address Alice key, like so. And then we handle errors by terminating the program in case any of these fails. So log fatal error, and if error is not nil, we log fatal error, and then we can print the we can print Alice's address to the terminal. So if we run this program again, we can see that the program is currently only printing Alice's address. And then we are going to need the Alice's key as well, and we are not going to need Bob's key because Bob is only going to be on the receiving end, so we do not need we don't need his private key. But anyway, we can still write a function. Oh, you know what? I'm just going to do the same thing twice. So, yeah. So Alice's Bob's key and error equals derive master secret key base and with the byte size of Bob. If it fails, we abort, and then Bob's address is derived from Bob's key, and then we can print Bob's address as well. So what's going to happen is that this address is going to send some money to the other one. And I actually have this idea that maybe we could also derive another address, because if we generate too many blocks, then Alice is going to have a heckload of money. And we don't want Alice to actually have a heckload of money. We just want her to have some money that she can send. Otherwise, it's going to get like a Bitcoin pizza night. So I'm also going to derive a third address. And at this point, it's becoming very repetitive. So I'm just going to write a helper function called must derive address. And then I'm going to pass the base and salt, which are bytes, and it's going to return a BTC util address. And then it's basically just going to do the same thing as in here, base salt, and then address error equals master to address key. If this fails, we log fatal, and then we return the address. And this way we can kind of clean it up. So Alice's address, we still keep Alice's address because we're going to need it to send funds, but then Bob's address can be just a must derive address with a secret key base, and then the string Bob, and then the bank's address, it's going to be bank. And then I'm also just going to rerun all of this with Alice address equals must derive address, and that's going to be Alice's address. So I'm printing Bob's address and Alice's address and bank address, and I could print them like in a nicer format. So printf Alice and then tab, and Alice's address, and then this is going to be Bob, and then the bank. So now if I run this program, declare and not use Alice key. Okay, I'm going to keep it for now. So now we have 3 addresses, and we can see that Alice's address hasn't changed, Bob's address hasn't changed, and we now have a third address that belongs to the bank. And now we can spin up a local Bitcoin node to actually generate some blocks. But before this happens, I'm going to commit, generate some addresses. Okay, and now I'm going to start a local Bitcoin node using Docker and Docker Compose. So if you don't know Docker, that's a pretty simple tool that runs containers, and containers are like tiny virtual machines that you can use to run programs in isolation, and it's based on the Linux kernel. And I'm going to most people in the industry know what it is, so I'm not going to go into too much detail. And we define a Docker Compose file, and we're going to have a Bitcoin service that's going to use the image Bitcoin/Bitcoin version 29.0. We're going to expose a port, and that port is going to be 18443, and it's going to map to the port 18443 in the what's his space on localhost, and we're going to run it with some parameters. Rectest1, RPC user is going to be username, and then RPC pass is going to be password, and RPC allow, what was it again? RPC bind, okay. We need to tell it to bind on 0000, which means it's going to expose the API on all interfaces and not just on localhost. And then RPC allow IP, we're going to have to tell it to allow connections from outside of localhost, because it's going to be running in a container, and the container is considered a separate machine. No, it's called RPC password and not pass. Okay. RPC allow IP equals this, and rectest is this, print to console and server equals 1, like so. And then we're going to attach a volume, which is like persistent storage, and you're going to use just a named volume, and you're going to attach it to home Bitcoin /.bitcoin, like this. And we're going to use this path even if you're on macOS, because the container itself is running Linux, and I think that's enough. And we have to define a volume called Bitcoin in the volume section. So now if I run docker compose up, additional property volumes is not allowed. Okay, it's called volumes, like this. So now we have started, we now have a node running, and before we are going to make calls using the Bitcoin CLI, which you can install. I think I have installed it using Homebrew. Which Bitcoin CLI? You can install it using Homebrew, and this way you will end up with 2 installations of the Bitcoin core. But this is a sacrifice. This is a sacrifice I'm willing to make, because the program is pretty small. And we need to define a Bitcoin conf file, and we need this file to look like this with rectest1. We need to have this running local. We need this file locally in home/.bitcoin/bitcoinconf, because this way it's going to set the default parameters for Bitcoin CLI, and without this we would have to specify the rectest. We would have to specify all of these parameters every single time we call Bitcoin CLI, which is going to be a pain in the neck. And if you are on macOS, the configuration file is in a different location. It's at home library application support Bitcoin, and here I have included a neat little script which can create this configuration file for you. So now we can run Bitcoin CLI get blockchain info, like so. And I think this is almost always going to print, oh, you know what? I'm going to start from scratch. No, sorry, I think I'm running an older, I'm running an experimental, what was it? Yeah, why is this here? Okay, I'm going to stop my node because it's not clean. Docker compose down, docker volume ls. I'm going to take this, docker volume rm, and if we docker compose up again, we're going to start with a fresh blockchain, and I think this blockchain is going to almost always be the same. I'm not exactly sure. Anyway, we now have a clean blockchain, and we can send some money to Alice, and we can do this Bitcoin CLI generate to address, and we pass the address, and before the address we need to pass the number of blocks. So we generate one block and the reward goes to Alice, and now it means that she's going to have 50 Bitcoin at her address, like she's rich, and but we can't really get any unspent, we can't get a list of unspent transaction outputs because we do not have a wallet. And let me quickly explain what this unspent transaction output means. So in Bitcoin, the money is not in your wallet, it's not really on the blockchain. The money, the remaining balance in your wallet is going to be the sum of all unspent transaction outputs. And if we go to some blockchain explorer and look, for example, at this Bitcoin Pizza Night wallet. So okay, there is this blockchain explorer, and we can actually look at that particular block because it's forever visible on the blockchain. It was block 57,043. So 57,043 block, this block on Bitcoin, and there was one transaction in this block, and it was this one. We can open this and we can see that the transaction consisted of a lot of inputs. I think there are 131 inputs. So this means that this guy who sent this, the man who sent this 10,000, the man who sent 10,000 Bitcoin for 2 pizzas had like a lot of addresses, and it was sent to this Jeremy's third event. And we can see that this address currently has 270 US dollars in it. And this number, like the number of all of this, the number of this number is the sum of all of these transactions which have not been spent yet. So every time you spend a transaction, it's like the total sum of the transactions is deducted from your wallet, but you can send a part of the previous unspent transaction output back to yourself. This is called change. And this way you like that spent transaction is going to be deleted from your balance forever, but you will have just a little bit less money, but you will still have like a new UTXO. I'm sorry if this is a bit convoluted. I'm not great at explaining this. So we, as we can see, we cannot back to the video. We can see that we cannot list unspent. We cannot check the balance for Alice because we do not have a wallet. and we can create a new wallet using create wallet. And okay, Bitcoin CLI create wallet. Then we pass a name for the wallet. I'm going to call it watch only because we are not going to be storing any private keys in it. Then we call it true. When we call true, the true is blank, so we're not going to generate a default address. And then it was, the second argument was disable private keys. We're not going to be storing private keys and we do not want a default address. Then we pass an empty string because we do not want a passphrase. Then I don't know what avoid reuse is. Like avoid reuse is related to privacy and we don't really care about it. Then the sixth argument is called descriptors, and it means that it's going to be using descriptors to track addresses. And that's like a newer version to track addresses inside of Bitcoin Core. And then finally, the last argument is load on startup, which means that effectively this is going to be the default wallet and it's going to be loaded when we restart the server. So we have created a wallet. We got a warning, but as we can see, it was created. And now we can try and import Alice's address into the wallet. So Bitcoin CLI import address, and we paste this address, and we're getting the message that we cannot import this address because it is a SegWit address. It's not, we can only import legacy addresses into the wallet. Like I think we could import this one. Not even this. So no luck here, but we can call another command called import descriptors, and this import descriptors command, it takes a JSON payload. So we're going to need the address, and this address I'm going to store it in a shell variable like this, and then the payload, it's going to be a JSON array like this. No, sorry, we cannot use a single quote. We need to use a double quote. Payload equals double quote like this, and then the descriptor is going to be addr for address, and then we add this address. And sorry, I forgot to escape these double quotes. And then we need to pass payload like this. Then we need to pass a timestamp, and this timestamp is going to be, it's a number. It's either a Unix timestamp as a number or the string now, and I'm just going to get to fetch current timestamp minus 2 hours, like so. So this is the timestamp that we start from, and then we pass a label, and the label is going to be the address, like so, and then we close the payload. Okay, what does the echo payload say? Okay, looks correct. Let's try to import it, and we will see Bitcoin CLI import descriptors payload. missing checksum. So this is, we cannot really import the descriptor like this, even though this is mostly a valid descriptor, but we need to calculate a checksum. Now the easiest way to calculate a checksum is to call Bitcoin CLI get descriptor info, and then we pass the descriptor like so address. So now we got the Bitcoin CLI gave us the calculated descriptor checksum, and we can extract it using JQ like this. Wait, where is my JQ coming from? Which JQ? Okay, JQ. Are you sure? Oh, sorry, it's like this. That JQ-R descriptor. So this is going to fetch the JQ, like the descriptor property from this JSON payload. And JQ, you may have to install it using Homebrew or your Linux distribution's package manager. So I'm going to store this descriptor in a shell variable, like so, echo descriptor. Okay, and then we can modify the payload. I used to import it, descriptor, like so, echo payload. Okay, this looks correct. Now let's submit it. Bitcoin CLI import descriptors payload. Okay, great. So we have imported this payload, and now we can try and call Bitcoin+CLI list unspent. And we at least we're not getting an error, but we don't have any unspent transaction outputs. And the reason is that we can see, if we look at the transaction that gave us this 50 Bitcoin, is that it's called immature, and immature means it doesn't have enough confirmations. This transaction was a result of a mining reward, and if you create bitcoins by mining them, then you have to wait until this block gets 100 confirmations before you can actually spend this money. And this is because forks can happen. So you mine a block, and then after a few blocks, like, it is possible that 2 blocks are mined at the same time and they are different, and then people will be mining based on those blocks. And if it happens, it is called a fork. It's like usually unintentional, and then you need to wait until like one of those forks wins before you can actually spend the money you got for mining. And great. So before we can spend this money, we need to generate more blocks. And this time I'm going to generate them to the bank, because I do not want Alice to have so much money. So Bitcoin CLI generate to address. I'm going to generate 100 blocks with the address of the bank. And this was instantaneous. And now if we try Bitcoin CLI list unspent, we can see that we now have 50 Bitcoin in our wallet, and that this block has 101 confirmation and it's spendable. So at this point we can finally try and create a transaction. So before we create a transaction, we need to know the details of our unspent transaction outputs, and we can do this using an RPC client. And in order to set up an RPC client, we need to install another package. That's from my notes. Yes, we need to install this package, RPC client. It's not in the BTC util, so go get. And in the meantime, we can set up a client like this. And I'm just going to do this in a helper function. So I'm going to call it func init RPC client and return client. And it's going to return a what's happening right now? Okay, we have an error, so okay, I need to import this and import this library, and it's going to return a pointer to RPC client.client. So RPC client.client, great, and I'm just going to initialize it here. Client equals init RPC client, and then in here we can fetch client dot list unspent, and actually you could just call list unspent, but a more fancy way, if we wanted to actually check that the money belongs to Alice, is we can call it min-max addresses. And then it takes like the minimum count of confirmations, and it takes the maximum amount of confirmations. And the maximum amount of confirmations is, I think, this number. And we can also represent it as 10, what was it? 10 million minus 1. Like so. And then we pass a list of addresses, and we can pass Alice's address like so. If there was an error, we are going to log the error and log fatal. We abort the program, and then I want to write a function to pretty print the unspent thing. So I'm going to define a function called pretty print, and it takes anything. And then output error equals JSON Marshall indent v no prefix and a tab. If error is not nil, log fatal error. Otherwise, fmt os write os std out write out like this. So pretty print unspent. And maybe I should also quickly go over the RPC client configuration. We are passing the localhost port 18443, which is the default port for regtest. We pass the username and password that we have specified in Docker Compose. When we disable TLS, because we are on localhost and we do not have a reverse proxy, and HTTP post mode is specific to the Go library, because they also have their own implementation of the Go RPC server, and it uses WebSockets by default instead of a JSON HTTP based API. So here I specifically specify that I want to use the HTTP client. Okay, let's run this program and see what we get. Okay, we are getting, I think, okay, this is too ugly. I'm going to use 2 spaces instead. Okay, so we are getting, we get a transaction ID, and this transaction ID is the same as we get with Bitcoin CLI. Then we get the address that the transaction was sent to. Then we get this script public key, which we are going to need in order to spend this money. We get the amount, and we get if it's spendable. Okay, great. So this way we now have an unspent output, and we can first we can validate if length of unspent is equals 0. We can log fatal, no money to spend, sad face. But we do have an unspent transaction output, and we can just assign it from here, like so. And now I have to look at my notes because I kind of forgot what I did afterwards. I think we're going to need these are my notes. Experimental on the branch WIP RPC transaction main.go. Okay. So we are creating a new transaction. I'm going to call it TX because we call a package called wire, and this wire is a new MSG transaction with a wire TX version. And this is from package BTC Suite BTCD wire, and it should be automatically imported in this package if you have your IDE correctly set up. Then in this TX we add transaction input, and we're going to call wire new transaction input and wire new out point, and that's okay. And before we can specify it, we need to parse the transaction hash we get in here into binary, and it's due to endianness reasons this is actually reversed. So we can call it UTXO hash, ignore the error, equals chain hash, new hash from string, new hash from string, UTXO transaction ID. Okay, and we specify this UTXO hash and UTXO's the out, and the out is the index of like the output index, but was actually directed to us. So if you get money, for example, from Binance, okay, like on Bitcoin. Okay, well, anyway, if you get money, for example, if you get some money from, okay, this one has 5 outputs. So if there is money sent to multiple outputs, this is going to be output 0, this is going to be output 1. These are 0 indexed. And you need to specify which of these outputs was actually your address. And this is returned by this vout parameter. So we specify this is this vout, and then we have, so the first argument to new transaction input is this out point, and then there are 2 parameters, one which is nil, which is signatures, and the one is witnesses. Signature script and witness script. Okay. I'm not exactly sure if this is like the most correct way to do this, but this worked, so I'm just going to leave it at this. And then we need to calculate the total amount of what we have to spend, and total amount equals UTXO amount. If you have multiple UTXOs, you need to sum this, and the amount we got from the API is actually in Bitcoins, and we want the amount in Satoshis, which is times 2 to the power of 8. So we have to multiply it by 8 million, by 100 million, 10 to the power of 8, yes, 1 to the power, 10 to the power, 1 times 10 to the power of 8. And the amount we want to spend the transaction amount. Let's say we want to send 1 Bitcoin to Bob. And then let's say the fee is going to be 500 Satoshis, which is reasonable, and we're not going to go into fee calculation in here. But since the transaction is only 1 input and 1 output, it's 1 input and 2 outputs, it's going to be pretty small. And then we can calculate the change. The change equals, total amount is this. We can convert it to int64. Then this is also going to be int64. And this is also going to be int64. This way we don't have to convert between types. This is going total amount minus transaction amount minus fee. Great. Okay, then we need to specify the output address, and the output address is going to be Bob's address. And then we can see add transaction output, and it's going to be we need to generate the so-called pay to address script for Bob. So I'm going to call it output script, and this also returns an error which we can ignore. TX script pay to address script. And then this is going to be Bob's address, and we add transaction output, which is going to be wire new transaction output, and that's the transaction amount, which is 1 Bitcoin, and the output script for Bob. And then we want to specify a second output, which is going to be the rest of the money. It's going to be the change. So I'm going to call output is pay to script, pay to address script again. Call it tx script pay to address script, and that's going to be Alice's address. And I'm going to add a new output, and that's going to be the change, like so. Great. So now we have the outputs, and then we can sign the transaction. And in order to sign the transaction, we need to have the public key of for the previous for the UTXO, and that's going to be UTXO public key script equals hex decode string UTXO public key, and then we need to so we are going to be calling this tx script witness signature to generate a so-called witness, and that's tx script witness signature we pass the transaction itself, and then we have to call TXScript new transaction signature hashes, which takes the whole transaction, and then the second argument to this new TXSig hashes is a previous output fetcher, and that's an interface, and there is a special helper function called new canned previous output fetcher. So input fetcher equals TXScript new canned previous output fetcher, and that takes the UTXO public key script and the total amount, and we pass this input fetcher to this function. Then the witness signature. Okay, what's the third argument? The third argument is index. So we are generating a signature, a witness signature for the 0th input. The amount is going to be the total amount for this specific UTXO. And then the subscript is going to be zero UTXO public script. No, wait, what? Okay, 0 total amount and then UTXO public script. I think so. And then we call a flag TXScript signature hash all with Alice's key. And we cannot call it like this yet because this Alice key is currently an extended key, and we want Alice's private key is going to be the result of calling Alice key EC private key, like so. We just ignore the error because we know where this private key comes from, and there shouldn't be any error. And then we can let's see if there was an error when creating this witness signature. We report it and abort, and then for the transaction, for the first input in this transaction, we specify the witness to be this witness. And I think this may be a bit more complicated. This would probably be a bit more complicated if we were doing a multi-signature transaction, but for now this looks correct. And okay, so we have set an input, which is the transaction that gave us this 50 Bitcoin. Then we have specified two outputs, and one is Bob's address, and we send him 1 Bitcoin, and then the second output is the change. And then we did all of this to generate a SegWit signature. And then the next thing that's going to happen is we're going to serialize it, and the TX serialize function needs an IO writer. So we are going to write it into a bytes buffer, and then we can print the transaction as hex, like so. And I think there was some other print. Okay, I don't think so. Okay, so let's see what this returns. So we have generated a transaction. This is what a transaction looks like. They are usually transmitted in hex format. And then we see that if we run it again, it should be more or less the same. So I'm going to store it in a variable. Transaction equals the result of calling this command. And then I'm going to call Bitcoin CLI the code raw transaction. no, sorry, Bitcoin CLI decode roll transaction, and that's going to be the transaction like this. And then Bitcoin CLI decoded this transaction for us and gave us like a new transaction ID, a new hash, and these are the inputs. So the input is indeed the previous transaction ID. It ends with C6, and there are witnesses, and then there are two outputs. One is 1 Bitcoin and the other one is the change, and this is going to be sent back to Alice's address, and this is going to be sent to Bob's address. So now we can, I wrote a helper function called validate transaction, but actually the first part of validating a transaction is calling decode row transaction, and that's what we have already tried, and it seems to work. And then we can call test mempool acceptance. Test mempool accept. Like this. Oh, and it wait, what? Okay, so we need to pass it as JSON, like so, because this takes an array. So we can see that the transaction could be allowed to the mempool, and the mempool is like the queue of Bitcoin transactions that are currently waiting to be mined. We can see that it is allowed. We can see that the V size was calculated to be 141. That's like the virtual size of a transaction once it's stored on the blockchain. And usually the transaction fee is calculated based on the V size. And we can try and send this row transaction. So there was another RPC called send row transaction. And then we can just pass this transaction hex, and that just returned as the ID of the transaction. And then we can see that this ID was also logged in this in the wallet, because it says it's new in mempool. And we can, if we call Bitcoin CLI list unspent, we can see that we have already spent it. But there is a transaction, and this transaction is okay. So which one is this? This is our. So this is the first transaction that we got. Then there is the second transaction, which is the change. And the third transaction is that we are spending this money. And we are spending this. So yeah, we can see that we are receiving money from our own transaction. Yes. And at this point, this has 0 confirmations, which means that that Bob hasn't got the money yet, and that Bob has not gotten. Bob cannot spend his money yet, and we cannot send any new transactions. So we need to generate another block. So I'm going to generate another block for the bank, like so. And now if we list and spend, we can see that we have less money, specifically 50, we got our old 50 Bitcoins, but it's now diminished by the one Bitcoin we sent to Bob, and by the 50 Satoshis transaction fee we sent as fee. Okay, and we could also try and see the actual, the actual, what was it? Okay, so right now we don't really have, if we go to these transactions, we can actually get Bitcoin CLI get raw transaction like this. We're going to also need to specify the block address in order to be able to fetch it. So this was mined in the last block. Wait, where is it? This is receive. Okay, we mine it in this block. So now if we can call get raw transaction with the transaction hash and the block hash. Wait, what? Get raw transaction Bitcoin RPC. Okay, if that's the second argument is they're both. Okay. So we called Bitcoin CLI get raw transaction. The first argument is the transaction hash. The second argument is true, which means that we want the transaction return in JSON. And the third one is the hash of the ID of the block in which the transaction was mined. And we can see that it was sent from the first transaction, the mining transaction. It had a witness, but it doesn't really list an address. And then this was sent from, the change went to Alice, and this was Bob's address. So we can take this descriptor and we can import it into the wallet. So Bitcoin payload descriptor. We want to import this descriptor into our wallet so we can see how much money he actually has spent. So payload is going to be, this is an array, and descriptor is going to be this descriptor timestamp is going to be 2 hours ago. We need to pass an older timestamp so it can be, so we can still get so we node will still index this transaction, like the transaction we have just received. And then the label I'm going to specify as the address itself, like so. Bitcoin CLI import descriptors payload. Okay, so now if we try Bitcoin CLI list unspent, list unspent, okay, we can see that there are currently 2 unspent transactions in the wallet. The first one was sent to Bob. This is Bob's address, and this is Alice's address. And so we can see that Bob has 1 Bitcoin now, and he can spend it. And we can see that Alice has almost 49 Bitcoins and she can spend it. And so in this demo we used the regression testing network, but you can use the exact same technique to also sign transactions in the real main network for blockchain or in the testnet. And the only thing you're going to have to do is you will have to swap this network params for mainnet or something. And thank you for watching. If you enjoyed this video, please consider subscribing to make programming fun again. And there are also more videos about Bitcoin in this playlist. And if you really enjoyed this video, you can also consider subscribing to my, signing up for my Discord waiting list. And if we hit 100 sign-ups, I will start a Discord server. And then in the meantime, thank you for watching, and I will see you in the next video.